today's topic, which is really the general linear model that we use for estimation of the evoked hemodynamic response. And also it allows us to simultaneously deal with filtering of physiological interference. Stop me at any time with any questions. So, if we look at just some raw FNIRS signals, really from anywhere on the head, look like this. So we just see lots of fluctuations. This is over 100 seconds. So you can see, typical colors: red is oxy, blue is deoxy, green is total hemoglobin. We see cardiac oscillations in oxy and total, not really in deoxy. And we see lower frequency fluctuations in oxy and total as well. So all of this physiological variation is really interfering with our ability to estimate the brain activity patterns. So we really want some good ways to deal with those fluctuations. So those lower frequency fluctuations are comprised of vasomotion or Mayer waves that happen around 0.1 hertz, respiration, which maybe is happening around 0.2 hertz, cardiac frequency is around 1 hertz. There's random measurement noise from the instrument. This could be electronic noise or shot noise. Then there could be motion artifacts. Finally, there's our functional signal that we want to measure, the brain activation pattern, right? So you can see the frequency content of that hemodynamic response is overlapping with these low frequency physiological oscillations, and the amplitude can be comparable. So this presents a challenge if we're trying to do some signal processing. All right, so how do we extract this hemodynamic response function? So, one is experimental design. There's simple approaches. We do a repetition of stimuli, and the idea is the hemodynamic response to the stimulus is time locked with the stimulus, and maybe the physiological interference is not. And so by repeating the stimulus, we could average out the confounding influence of those physiological oscillations. But there's always a possibility that those systemic oscillations could also trigger, synchronize with the stimulus. And so one way to get over that is you can jitter the timing of the presentation of your stimulus. This particularly works well if you're looking at brief stimuli that you can present kind of rapidly in a randomized fashion. Essentially looking at like event-related potentials. You can use bandpass filtering. So low-pass filtering works certainly well at removing the cardiac signal and also just higher frequency instrument noise. So that's very effective. High-pass filtering, you can use that for removing instrument drift or very low frequency physiology. I just always add, I personally don't like using a high-pass filter. I instead like to put a drift correction into the general linear model, which essentially does the same thing as a high-pass filter. And we'll discuss how to do that in this general linear model. Okay, so these are the sources of physiological interference. Low-pass filtering works well on cardiac signals. Low-pass filtering also works well on measurement noise. It's unclear what to do with vasomotion and respiration, just because the frequency content is overlapping with the functional signal that we want to measure. So we can try just experimental design approaches and some signal processing approaches. Right. Okay. And if we don't deal with this, it can lead, particularly if this systemic physiology is synchronizing with the presentation of stimulus, it could end up leading to false positives in your estimation of brain activity. So one just has to be careful about that. Motion artifact, I believe that's the topic for tomorrow. We have correction algorithms now for looking at motion artifacts that are working well. So we'll talk about that tomorrow. Again, just interrupt if you have any questions. So here's a subject that was doing a right-hand motor activation task. It was block averaged. One channel is over the motor cortex, one channel is over the prefrontal cortex. Of course, on the prefrontal cortex, we did not expect to see brain activation. So this is most likely some systemic physiology that's synchronized with the stimulus. So what often happens with some motor task is you'll actually get an increase in heart rate, which will modulate blood pressure, which modulates the oxyhemoglobin in the arterioles and blood volume. It can look very much like a brain activation pattern. So that's an example of systemic physiology synchronizing with the stimulus, right? And not just motor tasks, but any task actually that has a startle response that maybe startles the subject could also give rise to a momentary change in heart rate that could produce a response that looks like brain activation.
So in this slide, which one looks right and which one looks wrong to you?
Well, that's the problem. You know, that they both could be right.
But you're saying that one might represent more of the physiological response.
Exactly. And so this is the problem we're dealing with, right? So we want to come up with methods that allow us to distinguish or filter out the confounding signal. Now, what helps us here is that heart rate response, that blood pressure response is predominantly, it seems, producing hemoglobin changes in the scalp and not in the brain. So this is why the short separation regression, as we'll detail during this lecture, is so effective at helping us distinguish which of these time courses is the brain response and which one is the confounding systemic physiological response. But without that sort of discrimination of scalp signal from brain signal, we wouldn't know. Okay, so before we get the short separation regression, I mean, there was like a decade where we were trying many different methods to try to deal with this physiological interference. And for a few years, we were quite excited about using independent measures of the systemic physiology. So we had a pulse oximeter giving us the PPG signal. We had a respiration belt around the chest giving us the inhalation, exhalation. And we had a blood pressure sensor, just a pressure pad on the fingertip, which was giving us traces of the blood pressure. And the blood pressure in particular, you could see in the red line measured from the fingertip, correlated incredibly well with the optical signal we were measuring from the head. So, this is when we started to realize, geez, we are very sensitive to blood pressure changes, right? So, and basically what's happening is as the blood pressure changes, is just changing arterial blood volume in the scalp. And we're very sensitive to scalp hemoglobin concentration. So that this is what we're seeing here. And so we investigated actually using this red line from the blood pressure trace as a regressor in a general linear model, published in these papers, that idea, and it worked very well. So if you record these auxiliary signals, we can bring them into Homer and incorporate them into the general linear model. But to do that, of course, you need to have those independent measurements. There are nice devices out there. We use the BioPack devices for this, and it works very well. Over the years, though, we just stopped using it because it was just additional experimentation, instrumentation that you needed to put on your subjects. Those instruments would have some potential of not working well, not giving good signal, and it was complicating the measurements. And short separation regression came along and proved just to be much easier to do routinely, and so we stopped using these independent measurements of systemic physiology. And while Homer does indeed support it because we used it over 10 years ago, I'm sorry, but we don't have exercises showing you how to do that because we find the short separation regression is so effective. But I mean, if anybody wanted to figure out how to do that, we'd be happy to discuss it on the forum, how to use those independent physiological measurements. So short separation regression, this idea was first published in 2005, and then our group started to look at it further a few years later, just to really integrate it with the general linear model. So the original paper actually would do the short separation filtering first and then estimate brain activation. What we started to do was really show that it's much more effective to estimate the brain activation and filter the scalp signal simultaneously. That really reduces your potential of filtering out brain activation patterns. So the idea, is all based on this fluence distribution. You have a source of light. Light is injected into the head. It scatters everywhere, decays exponentially with depth. Of course, what we're really interested in is the light reaching our detector and the sensitivity profile we have to absorption changes between the source and detector. And so typically we use like a 30 millimeter separation, and we do that so we can get sensitivity to the brain, right? So if we use a smaller source detector separation, our brain sensitivity is reduced. So, here in this simple geometry representing the layers of the head, we calculate with a 3 centimeter channel separation, our relative brain sensitivity is 8%. So like 90% of the signal is coming from outside the brain, and only 8% is from the brain. If we make that channel separation, say 8 millimeters, then only 0.4% of the signal sensitivity is coming from the brain, right? So this gives us the idea. We can just use a short separation channel to measure what's happening in the scalp. And the long separation channel, which is nominally measuring the brain, but is mostly measuring scalp, what we want to do is filter out the scalp from this long separation measurement. And GLM will allow us to do that. Okay, this is just more pretty pictures showing the same idea. We'll make the short separation measurement simultaneously with a long separation measurement.
Can I ask a question here? Is there a different amount of time that it takes for the light to go from the source to the shorter channel and then the longer channel, the 10 versus the 30?
Sure. The light does maybe, it's a nanosecond on average to get to 10 millimeters away, and maybe, actually probably half a nanosecond. And then this is like 1.2 nanoseconds to get the 30 millimeters. But for, most measurements, that doesn't matter because we're just measuring the amplitude of light, and this time scale is so fast. Yeah. Right, we're not sensitive to that for most F-NIRS measurements. For a time domain F-NIRS measurement, that's a different story, as we discussed on the first day. Okay. So, here's example measurements at 12 millimeters and 30 millimeters. You can see they look quite remarkably the same because they're, this is only mostly scalp, and actually both of them are mostly scalp, right? And so that's why they look pretty much the same, right? But we want to figure out where the brain activation signal is in this 30 millimeter measurement. Okay, so we do that by building a linear model. And this is called the general linear model. So we're going to model our measurement at a long separation. So Y would be a time series of measurements, right? So this blue line would be in a vector Y, right? We're going to say that that's going to be equal to some time vector of the signal from the brain plus some time vector of the signal from the scalp, with some coefficients in front of them. Okay, so this is the cerebral hemodynamics, this is the scalp hemodynamics. We add them together. That's what we measure with the 3 centimeter separation. So typically, in our analysis of FNIRS data, we just assume this is 0, right? So kind of the historical way to do it was you would assume if I average enough trials, the fluctuations from the scalp average out, and so we can just assume that this is 0, right? With what's becoming now really the kind of a much more standard approach to this is actually to have a short separation measurement. The short separation measurement is linearly proportional to the scalp hemodynamics. And so we plug that into this linear model, okay? And so we and others have written lots of papers on this. So first we looked at what if we just have one short separation channel per hemisphere, and that proved to be very effective at modeling that scalp interference and allowing us to better estimate brain activation. We then asked the question, well, would it be better to actually have multiple short separation channels? And of course, the answer is yes, because it turns out that scalp fluctuations are not the same everywhere on the scalp. There are slight differences. And so it's better to get those local measurements of the scalp interference. And we even quantified, how much better do you do if you use a short separation measurement that's close to the long separation versus further away from the long separation. And so this is summarizing a lot of what is said in this paper. So you could go to this paper for the details. But basically we had resting state data, and we were adding known hemodynamic responses to that, and then trying to estimate the hemodynamic response with different types of short separation regression. And so we knew what the true hemodynamic response was, and so we could calculate the R-squared correlation between our estimated HRF and the true HRF, or we could calculate the mean square error. So we saw that if we used a short separation measurement that was further and further away from the long separation, that our R-squared would decrease, or our mean square error would increase. And we saw that by changing the time lag between the time series, we could get a slightly better estimate, but still not as good as if you used a short separation measurement close to the long separation measurement, right? So location matters, and the physiological contamination does vary over scalp locations. Now,
can I
we
interrupt real
yeah,
quick, David?
please.
I was wondering, because you mentioned that if you have it at different location, it's better to kind of get more localized measurement, I guess. But let's say if you have short separation channel in one hemisphere with different location in one hemisphere, but no short channel on the other side, would you say the measurement from the one hemisphere is transferable to the other one, or no?
It absolutely is. And so what you'll see in our GLM function, the option we actually tend to use is we used to use the channel that was closest, the short separation channel that was closest to the long separation channel. But sometimes that short separation channel may be very noisy. And if that's the case, you really don't want to use that in a regression, because then that transfers the noise to your estimates of brain activity. And that's not a good thing. So instead, what we do is, for a given long separation measurement, we choose the short separation channel that is most strongly correlated with the long separation channel. And so that's already built into the GLM function in Homer, and that works very well, right?
I just have a follow-up question with that. So you mentioned that the short separation channels can cause noise. Is that what you said earlier?
Well, I mean, sometimes that short separation channel will not have a good signal to noise ratio, right? So it will not be a good measurement of the scalp physiology, but it will just be noise. And if you use a noisy vector as a regressor in a filter, it can just add noise to your estimate.
Right. And how would you like detect that? You just look at the.
But the way we detect that is we just use the short separation channel that's most correlated, right? So the assumption there is not all channels, not all short separation channels are noisy, right? So if all of them were noisy, well then that wouldn't work well, right? So then if you want to protect yourself against that, we have objective ways of rejecting channels that are too noisy. And then if you try to do short separation regression, but you had no short separation channels, it wouldn't do anything.
Okay, right. Thank you.
Does that make sense? Yep. And
Can
so
I
as
ask
we
a
go
question?
as we go through the exercises, we can show you how to reject channels based on signal to noise ratio. Yeah. So go on, next question.
Will we discuss the pros and cons of where to place your short source detector? Or is this a good time to ask that?
This is a perfect time to ask that. I don't, I mean, there's, get it close to your long separation measurements, right? Is probably the best guidance, right? But be more specific.
Yeah, so I'm thinking about, say you have a reasonably dense array, then are you better suited to put your short source detector, say, around the outside of your dense array, or maybe place a couple within the interior of your dense array?
Yeah, right.
Tomato.
Right. So depending on how you implement a short separation, if you have a dense array, it can be difficult to add those additional channels, right? So, one thing we're beginning to do more as we go to dense arrays that cover a large area, we're no longer bothering. I used to believe I wanted a short separation channel that was 10 millimeters or closer, right? But as we're moving to these dense arrays that cover a large area of the head, it's kind of difficult to get those channels in there. And so we've been finding that we don't actually have to add them. We can just, in our dense array, maybe we have like an 18 millimeter channel, and we may have like 40 18 millimeter channels. So what we'll do in that case is take the average of all of those 18 millimeter channels, and that seems to be working very well, right? And again, the Homer GLM function allows you to do that, right? It's not as good, as maybe having those like 8 millimeter short separation channels, but it's almost as good. And experimentally, it would be very challenging to get those 8 millimeter channels in there, so you do the best you can.
David, how does that compare, for example, to using filtering approaches, like spatial filtering approaches? Is it better to just go with the average? Would that be your suggestion? Or?
Yeah, I mean, by spatial filtering, I think you mean a principal component analysis?
Yeah, that's what I mean.
Right.
Yes.
So, I mean, that was the first thing we did, in early 2000s, and we published that, and it worked very well in 30% of the subjects. So we were super excited because sometimes it worked incredibly well, right? But as we did it more and more, the majority of subjects, it was actually filtering out our brain activation, right? And so then it took us a few years, but we figured out that the times it worked really well was when the variance in the signal was dominated by the systemic physiology. And what a PCA does, which, I don't know of any other spatial filters, but so PCA, is it finds the vectors that explain most of the variance in the data.
Makes sense.
And
yeah.
so but that wasn't true in all subjects. In a lot of the subjects, the biggest source of variance was the brain activation. And so then the spatial filter removed the brain activation, right? So, and in other subjects, maybe the dominant source of variation was just random noise or motion artifacts. And so it didn't really help at all for dealing with systemic physiology. Right. So we stopped using spatial filters, 15 years ago. It is interesting. I think in the literature, maybe you're referring to some recent literature. I think people have been talking about it in recent literature.
Right. Yeah. So I was thinking in particular. We collaborated a lot with Joy Here's lab here at Yale, and they recently published a method for removal of the physiological signal. I think it was like a couple of years ago. And so I was thinking in particular about the method that they've been applying, but I have to look more into the details.
Yeah, I think in their case, right? In their case, they have like whole head coverage, I believe. And so they have, and so in that, as long as you have a large area coverage, the dominant source of variation over the entire head is not likely going to be brain activation.
I see.
Right.
Okay.
And so in that scenario, you do not run the risk of, you greatly reduce the risk of filtering out your brain activation with a spatial filter, right? So that is the reason we stopped using it, was because we, 15 years ago, we had smaller probes. And so we were 50% of the time filtering out our brain activation or greatly reducing it. But, now that people have whole head coverage, that risk is greatly diminished. And so that, excellent, you brought that up. So that is why we're seeing people investigate spatial filters again.
Yeah, that's very useful. Thank you. Yeah.
Right. Yeah.
David, if I can go back just a minute to what you were saying about if you had a dense array with maybe 18 millimeter separations. Am I understanding you right if I were to say it this way, that you were basically saying in that case, maybe don't use short separation channels at all, because essentially are you saying we would go back to that assumption that the scalp signal, we can assume it's 0, and while that's not probably 100% true, it's better because we have only 18 millimeters instead of 30 millimeters?
So no, so let me restate it. In these dense arrays, it's too hard for us to put in like an 8 millimeter channel. And so we're saying, well, what else can we do? Well, we have the 18 millimeter, and we know that that's seeing brain and scalp. So we want to be careful not to filter out our brain activation from the 30 millimeter channels. And so what we do is we don't assume the scalp interference is 0. What we do instead is we average all of the 18 millimeter channels. And so the idea is, if we have enough 18 millimeter channels from many different locations on the head, and we average them all together, that averages out any localized brain activation signal. And so then we're left with this average 18 millimeter signal that hopefully has removed out any brain activation signal. And then we can use that as a short separation regressor.
Has that been tested by research? Maybe.
I mean, so we have been testing that recently. We haven't published it, but we've just started testing that recently. And the reason this happened is because we started using NIREX systems, and we realized we could do high density probe arrays with the NIREX system. But NIREX also sells nice short separation channels, which works well if you're doing low density measurements, but it's very hard to add. It makes the measurements very hard if you add those short separation channels on a high density array. So, we said, we tossed up our hands, and what are we going to do? Well, let's test this notion that I just described to you. And those tests are proving fruitful. So Miriam, this is good feedback for Deja is investigating this, right?
How many channels are you referring to, David? Oh, sorry.
So Deja will have to publish this. Yeah. So Sarah, I mean, in that case, we're using 32 sources and 32 detectors, something like that. Right.
That's what we are using too.
Yeah. No, if it was a smaller area coverage, I would be nervous. But it's only working because we're now getting bigger systems that cover larger areas of the brain, so that when you're averaging like these medium separation channels, you can be confident that it's not mixing in too much brain, that it's helping to average out the localized brain activity. These are very advanced topics you guys are asking. This is excellent. Right. Okay. Keep asking the questions. But in the meantime, moving along, we even investigated, we originally put a short separation detector next to a source, and that worked well. Could just put a very small fiber there. So we even asked the question, well, and that's clearly measuring scalp overlap with the source, but the long separation detector also has scalp. So maybe it'd be better to put a source near that detector. We did that experimentally. It was actually much harder to get good signals for us, just with our system we were using at that time. One could certainly engineer something that would be more robust, but it was just proved challenging. But I mean, at the end of the day, what this does give better estimates of the brain activation, but it was just experimentally harder to implement. So for well over 10 years, we were using fiber short separation measurements on fiber-based systems. So these were our typical fibers used for long separation. There's a source, there's a detector, and then we put a small fiber right next to the source, 8 millimeters away. So we did this for over 10 years. But actually now we're moving to wearable systems and high density systems. So this is really becoming a thing of the past for us, at least. Okay, so of course, so this is nice work from Sabrina Brigadoy and Rob Cooper, kind of just looking at what is the typical thickness of the extra cerebral layer, the scalp, skull, and CSF thickness. So how deep is the brain in the adult versus the infant? And they use these models to then kind of calculate, how short does the short separation need to be? And so they look, say, in adults where maybe the long separation is 30 millimeters, and looked at different brain regions and, showing for those different brain regions kind of what source detector separations, short separations you would need to get a relative brain sensitivity, say that was like 10% that of what you had at the long separation, right? So remember, like on adults, maybe at 30 millimeters, you're like 10% sensitive to the brain. So if we want to hit this metric of 10% relative brain sensitivity for the short separation, that means that short separation is going to be 1% brain sensitive or less, right? So it would be 10% of 10%. So basically on adults, it was showing, kind of like this green color, you needed to be like smaller than 12 millimeters, right? So that's kind of the justification of why I was always saying 8 millimeters. I feel comfortable that that short separation channel is not seeing the brain. Right. So they went on and looked at infants and explored that question as well. In infants, just because the scalp and skull is much thinner, you need much smaller source detector separations to see only the scalp. As it turns out, however, because the scalp is so much thinner, the physiological interference you measure in an infant is greatly reduced, right? So I've not really seen compelling evidence myself that you really need to bother with short separation regression in infants. But I do know some groups are looking more and more at that to see if there's any benefit. Okay, so in Homer, we use a GLM. Actually, we renamed this. You should go back and change the slides. It's a Homer run _ GLM function. We'll see that when we open up Homer. And so we model the signal with many different components. And I'll show that here. So we have our measurement Y. That's what the long separation channel might look like. We're going to add a drift regressor. So we can add any number of polynomials. We'll typically go up to a third order polynomial. So there'd be a constant term, a linear term, a quadratic term, and a cubic term. added as drift regressors. We would then add our short separation signal as a regressor. And then we'd add in some representation of the hemodynamic response function. Right. So that representation of that hemodynamic response function, we have the stimulus onset, and then we can have a model of the shape of the evoked response. So in fMRI, the shape of the HRF is predetermined. They call it the canonical hemodynamic response. With FNIRS, we have a higher temporal resolution, so we can actually estimate the shape of the HRF from our data itself, and that's something we've always done ourselves. But I think more and more people are getting confident in the shape of the HRF measured by FNIRS. It should be very similar to that of fMRI. And so more and more people are just using the canonical HRF. And so Homer allows you to do both. So first off, we like to start off just using Gaussian basis functions. So we have a series of basis functions that we're using to model the shape of the HRF. And so we have a beta that we're estimating for each one of these basis functions. And so we can put that into, so if we put all of that together, this is what our design matrix would look like. You can basically see here all of the stimuli that are presented. So, we're doing a convolution, right? So we're modeling the long separation measurement with some matrix times the beta coefficients. And so that matrix will have all of the stimulus onsets convolved with the basis functions. We also have the drift term. So here's the constant drift term. There's the linear, quadratic, and cubic drift terms. And then here's the short separation channel, right? So we want to find the beta coefficients multiplied by each of these basis coefficients to estimate our long separation channel. Okay. So then by inverting this design matrix, and multiplying it and moving it to the other side, we can estimate these coefficients, these beta coefficients. Right.
David,
and so yeah, go ahead.
What determines how many rows of the basis functions you have in the design matrix? Is it determined by the longest time separation between the onsets?
This is confusing me a little bit because I usually have the design matrix before the beta. So this is the transpose of what I'm used to seeing. So in this case, the number of rows, right? But typically it would be the number of columns if it was in front of the beta instead of after the beta. So the number of rows is really determined by the number of regressors you use, right? So we always use 4 drift regressors and 1 short separation regressor. So that would be 5 rows. And then you have your basis function for the HRF. And so in this case, we might have like an HRF that's 20 seconds and we have a Gaussian function every second. So that would be like 20 rows for the HRF. If you use a canonical HRF, you just have 1 shape, right? So you're saying, I know what the shape is. So in that case, you'd have only 1 row that you would estimate. So as long as you're confident in the shape of the HRF, you're only estimating 1 parameter. That's going to give you more statistical power, right? But potentially, more bias in your result. So there's, depends how confident you are in the shape of the HRF.
Okay, gotcha.
David, on the Y vector outcome,
yeah,
that's going to be just time series data from 1 channel.
Yep, exactly.
Okay, and what's the timing of that? Like how frequently is it?
I mean, it could be anything. I mean, in our measurements, it will typically be like 10 hertz.
Okay. And can the Homer do a GLM where you would then become more complex and include multiple channels and make it more like a matrix than just a vector?
I mean, that's getting into like an image reconstruction analysis. So we don't, Homer is really doing channel-wise analysis. If you want to analyze multiple channels at the same time, that's really the image reconstruction, and those are things we're doing in Atlas Viewer.
Okay, thanks.
Yeah, I mean, there are certainly clever ways you could try to do it outside of image reconstruction, but I haven't really seen people playing around with those ideas.
But right now, you just do a GLM per channel that you're interested in.
Channel, yeah, exactly. Yeah.
I had two follow-up questions. One was
Yep.
related to the PowerPoint that you just mentioned before, if you're using a canonical HRF. So would that indicate that you'd need to increase your number of trials if you were to use that approach?
Wait.
'Cause you said if you use a canonical HRF, it will decrease your power.
Oh no, it would increase your power.
Oh, okay.
Yeah.
Okay.
Increase the power, right? Because you're assuming the shape of the HRF.
Gotcha. And then,
So, I mean, nominally, you could use fewer trials, right?
right. Okay. And then building off of Spencer's question, would it be possible, so maybe not within the framework of Homer, but to build like a hierarchical linear model to look at multiple channels at one time within a subject?
I mean, absolutely. So all of that could be done.
Okay.
We ourselves have not explored that, right? And I haven't really followed the literature enough to see if other people have done it. We'll see. Yeah, at the moment, I'm not sure how I would exploit that, but it's certainly worth investigating. So starting off with our simple Gaussian basis functions, right? So we get a weight for each one of these basis functions. We can then, basically multiply these weights by the basis functions, and this is our estimated HRF, right? That we would get from the GLM. Okay. So again, in Homer, it's called Homer R_GLM now. This is the old name. So there's many parameters that we'll go over in the demo. We need to define the time range of the HRF. This is exactly the same what we did in the block average. We went yesterday, we were going from -2 to 20 seconds, I believe. So you do the same thing with the GLM. You have a solve method. So the traditional way to do this is in ordinary least squares. This assumes that there's no temporal autocorrelations in the residual of your model fit of the data. You could put a value of 2 here, which is a much more advanced filtering method that tries to remove those temporal autocorrelations. It's a paper Ted Hubbard published about 12 years ago. And this gives you better statistics, but it takes much longer to run. So when we interact with our data, we always start off with the ordinary least squares, but when we want to prepare our final published result, we might change this to Ted Hubbard's method. Then we have define the basis function. We default with 1, which are the Gaussian functions, but we also have the canonical basis functions. You have parameters for the basis functions. You have a threshold for the short separation measurement. Start with 0 so that you would not do any short separation regression. I'll explain this in a little bit. This is how you decide whether or not to use the nearest short separation channel, the most correlated short separation channel, or the average of all the short separation channels. Here you enter the polynomial order for the drift correction. And we did play around a little bit for doing motion correction as part of the GLM, but this actually doesn't work very well, so we don't use this, so it's 0. Okay, so the basis functions. 1 is that set of Gaussians, 2 is a modified gamma function, which is convolved with the duration of your stimulus. 3 is a modified gamma function and its derivative. And 4 is the specific form of the gamma function that is in the fMRI-AFNI analysis package. So these are all various canonical HRFs that have been described over in the literature the last 30 years for fMRI. And so these are included in Homer as well. But you do have to set these parameters of tau and sigma that set the shape of your HRF. And so you need to have some knowledge of what to use for those parameters.
David, can you just briefly explain the concept of drift?
Of drift?
Yeah.
Yeah. I mean, the drift can have many sources. It could be just the instrument. Maybe the laser power is slowly varying over time. Or another source of very low frequency drift in physiology would be like the partial pressure of CO2 in the blood. That changes blood volume in the brain, right? So that can just physiologically vary over minutes. Likewise, blood pressure can vary over minutes. So those are all different sources of slow drift, either from the instrument or the physiology. And we could try to model that in a GLM, but it's long enough that for the typical brain responses we're looking at, there's really no temporal overlap. And so it's just easy for us to do a drift correction. I do see many people want to analyze results from stimuli that are maybe presented for a minute. And so in those cases, maybe you want to, it may be difficult to do drift correction because depending on how long of a data set you have, your drift correction may actually remove your 1 minute long brain activation pattern, right? So in those cases, maybe you might think about measures of CO2 and blood pressure that you could use as regressors. Right? Or probably what would be easier is maybe a 10-minute experimental design so you could do some low order polynomial drift correction.
Thank you.
Yeah. Okay. So this is just a nice picture representation of what Spencer was just asking, where we're trying to model all of this low frequency variation in the signal using a 3rd order polynomial. Please note, do not use high pass band pass filter if you're also going to do drift correction. This does bad things to your data. Or can do bad things to your data. Okay, so let's go through the demo now. Before we open up Homer, do people have any more questions they want to discuss?
I guess I was wondering, what's the implication of having like a temporal autocorrelation in your residual? Like what does that mean?
Right, I mean, so when you do statistics with a GLM, and so our GLM will estimate the statistics of the beta coefficients. That statistical estimation assumes that the residual has no temporal autocorrelations. Which basically it's assuming that like the variance in the data you don't model is statistically independent at every time point. But maybe your model doesn't do a great job of modeling all of the correlated variance in your data, right? And so your residual will have temporal correlations left in it. And in that case, the statistical estimate by the ordinary least squares GLM is not accurate, right? So there's 2 ways to get around this. So one way, the way we have been doing it the last decade is we are not getting our statistics from the GLM, right? We get our statistics from averaging the runs the estimates across runs and across subjects. So we look at the variation in the HRF amplitude really across runs and across subjects, and that's where we get our statistical estimate, right? So the GLM would give us the statistical estimate at the run level, right? But for the last 10 plus years, our group hasn't been worrying about that. If one wanted to do it at the run level, and more we're starting to do this, and more and more groups want to do it that way, then you have to remove those temporal autocorrelations, and that's where that more advanced method built into the Homer GLM that Ted Hubbard published comes in.
Okay,
and sorry, that's an advanced topic we don't really cover in this class. Although clearly the students are getting much more advanced. So maybe we'll have to include in future years. But the paper is there, so one can read the paper.
Just had a quick question. Could you go back to the concept of drift and what it means? Explain it a little bit further.
Right. So sorry, I'll probably just repeat myself. Just ask me what I can explain better. I mean, so one thing is a light source. The light source, the power of the light source can slowly vary over time. And that can happen because of temperature changes in the instrument, just causing the brightness of the source to change, or maybe the current being delivered to the source is changing. Again, that would probably result from temperature variations in the instrument, right? Those would be low frequency changes in the intensity, which would show up in your data, right? Temperature can also affect the responsivity of the detectors, right? Or maybe a probe is slowly detaching from the scalp of the subject. And so the coupling of light between the probe and the head is slowly varying, right? Or maybe the blood volume in the scalp or the brain is slowly varying for physiological reasons, as could happen just because blood pressure varies when you're sitting here, your blood pressure varies, or the CO2 in your blood can vary just by how much you're breathing in and out. And the brain blood vessels are very reactive to CO2. And so if the CO2 in your blood varies, it varies the blood volume in your brain. More questions about that? I'm happy to ask and be more specific if you have specific questions.
So drift just covers another group of unwanted artifacts.
Yeah, and maybe abstractly speaking, drift is all of the low frequency variation that's much lower frequency than the brain activation we're trying to measure. And so we can just remove it with these polynomial drift terms. Yeah, Emma.
I had an unrelated question, so if anybody else wants to jump in about this before I start, please feel free. So my question was actually back to, you were saying one way to deal with the temporal autocorrelation is instead of using the beta weights and like from the GLM, you carry, it sounded like you were saying you carry them forward almost like a summary statistic approach. Is that correct? So you're taking the average of the betas across the trials?
Oh, sorry, you're asking, you mean to remove the temporal correlations?
Yeah, so you had said that your lab averages the estimates across runs and subjects, and then you run the stats there.
Yep, exactly.
Okay.
So that's what we traditionally do, right? And so we do that by getting the mean of the HRF at each run. And then when we average across runs and subjects, we get the statistical estimate that way.
Gotcha. So, and you do that by running like a one sample t-test, or?
Yeah, exactly.
Okay.
Exactly. Yeah, exactly. Okay, great question. Okay, so let's go ahead and open up Homer. Oops. Let's see. So everyone should be opening Homer at this point. So you're going to want to go to the day 2 exercise. Sorry, this path is not exactly the same. I'm not sure what you see, but go to day 2 and let's go to SS demo 1. So, you know,
Day 3, right?
I already, sorry, day 3, sorry. All the days are running together for me now. Day 3, sorry about that. So day 3, SS demo 1. I've already put Homer into my set paths here. And I'm gonna just go ahead and launch Homer 3. Uh-oh. Uh-oh. Oh, what did I do wrong? Miriam, help. Can you run this?
Let me log in with a different computer.
That is, I'm going to, sorry guys, that is funny. I'm shutting down MATLAB. I'm just gonna restart MATLAB. Have other people, I'm presumably not everybody's having that problem.
I was able to get mine to open up.
Yeah, all right.
I had the same problem, and restarting MATLAB and setting my paths again fixed it. So
Okay,
hopefully
good.
that works for you too.
Yeah. Oh, it didn't work. Miriam, where do you stand?
It seems to be loading. Give me a second.
That is so weird.
Recording in progress. Recording in progress. Recording in progress. Recording in progress.
Miriam? Anyone else? I'm opening up a different version of MATLAB, see if that does that.
So David, this is my screen. I can just do, you can keep explaining and I'll just follow.
Let me take just 2 more minutes. Let me try MATLAB again. Let's just, I don't understand which version of MATLAB are you using, Miriam?
Mine is 2019B.
Yeah, that's what I wanted to go back to. I was 2020B.
Could be, yeah, because of that.
Yeah, yeah, yeah. But I had to reactivate 2019B, and that's just too difficult for me to do right now. Gotta remember too many passwords. All right, sorry everyone. So Miriam's got it open. And sorry, I have to, should have opened slides on my other computer. Sorry about that. I'm going to open the slides on my other computer so I can see both screens at the same time.
So after you select the demo folder, do you have to select the CFG file that's in there as well?
Select CFG file, yeah.
Thanks.
Kind of funny. I always test the morning before all the demos, and this is the first morning I didn't test. Go figure. All right, so everyone should be opened up here in the directory. If you oh, Miriam, I could probably just take control of your screen, right?
Yeah, sure.
That might be easier. Did you give me control? Yeah, all right. So people remember that they could go to change group to change to the SS demo 1, and then it will open up and be here. You know, you select a channel, you can view the data. We already have all the conditions there. This was Miriam, I assume this is a finger tapping task, right?
Yeah, 10 seconds of finger tapping, I believe.
Excuse me. So let's edit the, let's look at the processing options. Sorry, now I have to adjust because this is really small on my screen. Let's see. Okay, so we have a high pass filter, we have the low pass filter. So high pass filter is 0, low pass filter is 0.5. I don't like making that 0.5. I like making it like 3 because I always like to see the cardiac signal in the optical density data. If you make it 0.5, then it attenuates the cardiac signal in the optical density data. People like to use like 0.5 there because it gives them a more smooth HRF. But the GLM is going to smooth out the HRF for us. So as a result, we don't really need to use that low pass filter. For the OD to concentration, we were discussing for defaults, we like to use 1 and 1. So this was 6 because historically we used to always use 6 and 6, but today, you know, the field is conventionally now using 1 and 1. Here we can now look at each of the parameters for the GLM. So we have the time range, right? So we're doing that from -2 to 20 seconds. So if you look at, you know, slide 34, if you guys have downloaded that, you can see the parameters we're using, but I'll step through it. So T range is -2 to 20. The GM solve method, this is what I was talking about. 1 is the traditional ordinary least squares, and there's a citation for it. If you put a 2 there, you're going to get Ted Huppert's method that filters out the temporal autocorrelations. That takes much longer because it's an iterative process. So we recommend when you're doing the initial analyses, you just use 1, which is the faster ordinary least squares. So we put a 1 there. Then you have the index for the basis function you want to use. So we start with 1, which is a consecutive series of Gaussian functions. Later on, you could try out the different gamma functions if you want. So we have 1 there. The parameters you need for the basis function depend on which basis function you're using. So for the Gaussians, you need to specify the width of the Gaussian and the interval, the step between Gaussians. So we say the width is 1 second and the step between them is 1 second. So this, mind you, is going to impose like a 1 second temporal smoothing into the estimate of our HRF. If we wanted less temporal smoothing, we could make this maybe 0.5 and 0.5. And then there's more, Gaussian functions that have to be estimated in the GLM. Or you could make it more smooth by, say, putting 2 and 2. That would make your estimate of the HRF more smooth.
But do you lose some statistical power with the more, if you did half a second, you'd have more?
I mean, for each beta coefficient, you would, yes. But the way we do the analyses, like with the Gaussians, is we never look at the statistics of the beta coefficients for the Gaussians. We look at the mean amplitude of the estimate of the HRF for each run over some time range, right? That depends on the duration of our stimulus, right? And then we got that mean for every run, and we then get the standard deviation across runs and across subjects, right? Doing a simple t-test. That's the way we've been doing it for the last decade or more. So then you have a threshold for the source detect, the short separation. So let's set that to 0 initially. So we won't do any short separation regression. You have the flag for the method to use for the short separation regression. So this is where you have the option. If you put 0 there, it uses the nearest short separation channel. So if you hover over it, you can get that context-sensitive help. We don't like to use 0 because sometimes that nearest channel can be noisy. So we like to use 1, which is use the short separation channel that is most highly correlated with the long separation channel. Another idea is to use 2, parameter 2, which is to take the average of all short separation channels. So that's another option as well. There's option 3, which is a more advanced topic that Miriam talks about, introduces you to next week, which is something we recently published that performs even better than this straight GLM approach for short separation regression. Then here's the drift order correction. So we put a third order polynomial. Then there's a contrast vector. Miriam, do you want to say anything about the contrast vector?
Yeah, so this is for the GLM statistics that we mentioned, right? The beta estimates, the statistics for the beta estimates. If you want to have the GLM output statistical results comparing two conditions, you have to provide the contrast vector here. For instance, if you have 2 conditions, you can put like 1 and -1 to see like it, then you will have the statistical outputs in your math files. I'll also show the details of that on Monday.
Okay, great. All right, so those are the parameters. So now that we have those parameters, we can go ahead and do analysis at the run level for this one subject. So I say run. And we can look at the HRF for that condition. So there's oxyhemoglobin, there's deoxyhemoglobin. And so we can see an evoked response here. This cyan line is a short separation channel, and you can see that there is some small evoked response there, but it's not so bad. Now, if we want to actually let's go ahead and view plot probe here to see all the channels. So you can kind of see a localized response. So that seems to be working reasonably well. I'm going to export this plot, create another figure, because I'm going to want to compare this with the result we get with short separation regression. So now I'm going to go back and edit the options, and I'm going to change this short separation regression to 15 millimeters. So it's all channels that are 15 millimeters or shorter in distance are going to be called short separation channels and be available for doing short separation regression with the long separation channels. So for the regression, the nuisance method, I'm going to put a flag of 1 here, which, remember, that means it's going to choose the channel that's most correlated with the long separation. Okay, so now we can go back and run this again. And we see it's cleaned up the response quite nicely compared with what we had before. Right, so you can see, that these responses are now just a very, very clean response. Like you can see those kind of wiggles we saw before are now gone in the HRF. And so those wiggles were just systemic physiology from the scalp that was not being modeled by the GLM. But then when we add the short separation regression, it's modeled by the GLM, and it helps remove that interference from your estimate of the brain activation.
David, can I interrupt real quick?
Yeah, of course.
I was wondering can you go back to the edit option? I just have a quick question about that threshold that you changed earlier. For that method part where you put number 1, there's the other 2 options. Is it okay if you kind of go through real quick what are those 2 option are and when do we use them then? The 2 and the 3 one.
Yep. I mean, if you put a 0 there, that's going to use the nearest channel. That's what we did originally. We don't use that anymore, right? We just left it there for historical purposes. And the reason we don't use the nearest short separation channel anymore is because sometimes that channel is noisy. Maybe it just had, hair underneath that channel, and you just have a noisy measurement. And so you don't want to use that as a regressor because it's just going to add noise to your estimate of brain activity. So that's why we added option 1, which uses the short separation channel that's most correlated with the given long separation channel. So that's the one we mostly use. We then added option 2, which is what Joe Culver and his group have always used. And they use that because their short separation channels were like 12 or 15 millimeters. And so those are what we should call medium separation channels. And they don't necessarily, they see brain as well as scalp. And so we like to average across all of those medium separation channels, so to speak, to help reduce the influence of brain activation on that regressor. So 2, if you put a 2 there, it will average across all of the short separation channels and use that regressor. Does that answer your question?
Yeah. And then what is the last one then? The option number 3.
Yeah, that last one is an advanced topic. Miriam, you cover that next week, right?
Oh, okay.
It's on Monday. Yeah.
On Monday. Miriam will cover that on Monday.
Okay, perfect. Thank you.
Yeah. Okay, let's.
Can I ask a quick question? So
Yeah.
if we don't have, let's say that we don't have short channels, but we have a high density array, we want to use the average instead of the short channels. How would that be implemented in Homer?
So let's say your medium separation channel is 18 millimeters. I would say let's use a threshold of 19 millimeters. So it's
Oh,
going
no,
to grab.
I mean, in the case that we don't have short separation channels.
No, but you have high density array, right?
Yes, yes.
What is the smallest? What are the separations you have in that array?
It's 3 millimeters. Sorry, 3 centimeters.
Oh, they're all 3 centimeters.
Yeah, they are all the same, exactly.
Yeah, well, then what you have to do, I mean, we can try it here. This is a small probe, so it's going to remove brain activation. Let's just try it. So, I mean, the long separation is 30 millimeters. I'm going to say 35, and let's average all of them, and see what happens to what was a beautiful brain activation, the green line, right? So if I run that, you know, it's not as beautiful anymore.
Right.
But that's because it's a small probe. If it was a much larger probe, okay, this is curious.
I think amplitude dropped quite a bit.
Yeah, I mean, so that one activation channel is okay. It's just, you know, so it's not horrible actually. You see, so the green channel is, as Miriam said, the amplitude dropped, right? But just qualitatively speaking, it wasn't a disaster. Statistically speaking, it may be a disaster, but this is because it's a small probe. You have a large probe, right? And so you could do the exact same thing with a larger probe and it may perform perfectly well, right?
Okay, thanks.
I do worry though that, interesting, if your smallest separation is 30 millimeters, I would try to get short separation measurements in there. Certainly if it was near X, you could you could get the short separation channels in. You know, if it was or not short set, right? So
the problem that we have is that we started the study like a year ago, and at that time, Nerix didn't have short channels.
Yeah. I understand. Yeah, well, you could try it. You could try it. Just be careful that if the array is not large enough, you may be removing brain activation.
Right. Okay. Great. Thanks.
Okay, I wanted to just do the group average, and boy, we're running out of time for the exercise, but let's see, let me remove short separation regression. I'm going to do the group average. So I just run this for the whole group, goes through all the subjects. And there's, you know, our really nice estimation of brain activation, like plot probe. I mean, this works pretty well. I export the plot. So even without short separation regression, it works pretty well. But if I then go back, edit options, not at the group level, at the run level, and I throw in my short separation regression, and again now analyze at the group level. Right, so you know, you can see in this one example, the short separation regression gives a modest improvement, not much, but other examples you can get much better improvements. Okay, Miriam, you want to stop sharing? So I can come back. So that's it for the demo. We have now we have an exercise that you guys can work on. Right. Which is the next folder in that directory. So you can change to that directory, open things up. And so this was a these are 5 subjects from a study that Miriam did, looking at painful and non-painful responses to an electrical stimulation. And so it's this bilateral probe design over the motor sensory cortices and some probes in the frontal cortex. And there are two conditions. You'll see condition 1 is a non-painful stimulus. Condition 2 is the painful stimulus, and they're randomly ordered. Each stimulus lasts 5 seconds, followed by 25 seconds of rest. And so what we want you to do is we want you to remember everything from the last 2 days, build an appropriate processing stream, right? And show that only a global response is apparent without short separation regression, and that you get, the much better classic hemodynamic response when you use the short separation regression. And compare the innocuous with the noxious stimulus and answer the question, which hand was stimulated, right? Which you'll be able to tell by, which hemisphere you see the brain activation occurring in. Right, so these tips, interesting, we didn't cover this. Miriam, is this important? Prune channels and excluding periods of motion?
For the group level, probably it wouldn't matter. When we look at the group level, we will see the effect of short separation.
Yeah, but we didn't really discuss this. So initially, I don't think you have to worry about that. We've got 35 more minutes online today for you guys to work on